see the title, that programmable interrupt controller. Okay, let's wait 2 minutes so that other people can join. Only 8 students have joined. Okay. So the topic, you can see that programmable interrupt controller. It's a topic related to the integrated circuit that handles the interrupt controller, or that handles the interrupt operation in a computer system. So previously, in the previous semester, in microprocessor course, I've taught you that when any interrupt occurs, what sort of procedures or what sort of functionalities a microprocessor need to do. And many things need to do. Likewise, that the current code segment register and instruction pointer register needs to be stacked. Then current flag register value needs to be stacked. And this after pushing these all information into the stack, then the new subroutine on one interrupt service routine number, based on the interrupt service routine number, the microprocessor finds the new code or ISR, that is the interrupt service routine. It finds, then accordingly it executes that. And after completion of this, after completion of the related interrupt service routine or interrupt function, the microprocessor again retrieves the previous code segment register value, instruction pointer value, and flag register value. So these all are performed by the microprocessor, but there is an important thing in a interrupt scenario, that is the priority of interrupt. Microprocessor doesn't handle that priority arbitration or the resolution of the priority. Rather, some external IC, likewise that the number is given here, the 8259. This is a model of programmable interrupt controller. We say that PIC. So in this course, you have seen that PPI, that programmable peripheral interface, then PIT, programmable interrupt timer or interval timer, then PIC, this is the programmable interrupt controller. So today we will see that how a programmable interrupt controller help or assist a microprocessor to handle the interrupt operation in a computer system. Let's start. So this is the lecture reference, and throughout this, so far in this course, we have covered this part 8155, which includes both timer and input output operation. Then we have covered 8255. This is separate IC for programmable peripheral interface for making the IO operation only, or input output operation only, and the timer assist this 8255. This is the 8253 or 8254 timer, that is also being covered. So today we will start talking about the interrupt controller, and in this course our target is to complete the DMA controller and 8251, the serial IO USART controller, that is used for the USB related interface. So today we'll talk about the 8259 interrupt controller. Before that, we'll cover some theory. So you know that it's just a revision of 8255, that in 8255 programmable peripheral interface, we have two ports, port A and port B, that can be used as the input and output port. And we have another port, that is the port C. This is the port C. This can be used only to handle the handshaking signals, or it can be used as the interrupt port. So which pin can be used as an interrupt port? Any pin from the port C for group A or group B. And through that pin, the interrupt request signal, if you can recall that while we have studied 8255 PPI, I have shown you that one interrupt request signal are sent to the microprocessor through the bus. So here is the concept of how the interrupt request can be sent to the system. Now, how to connect multiple I/O devices? First of all, we can see that throughout in this course we have seen that okay, we can connect CAN bus, we can connect inter-IC bus, inter-IC bus, CAN bus. So this is a large scale system, this is a small scale system. So let's consider that in a small scale system, the devices can be connected through two wires, one through SDA and one through SCL, and SCL carries the clock information and SDA carries the data. But what if this is a design choice, or this is a connection establishment choice? But there are several ways that in those ways we can connect the devices or connect multiple I/O devices. Let's consider that. Let's see that, and then thereupon we will decide upon which one is the best. So there are two possible ways. One, we can use a priority resolver to connect them. That means everyone will be connected with a priority resolver, and we can use the interrupt as a generalized mechanism. That means this priority resolver, this is the important term, that today we are talking about 8259 PIC. So what is this? This is actually the priority resolver. Through this priority resolver, the interrupt request can be placed to the microprocessor, so that the 8255 or this priority resolver can taken out the burden from the microprocessor to resolve the which device got highest priority or which device got lowest priority. That will be decided by the priority resolver. More details I will talk about in coming slides. Okay, so there are several ways of using the priority or handle the priority. So you can see this is one system. This is one system, and in this system you can see that we have the microprocessor, we have a priority arbiter, or it is the priority resolver circuit, though we have not given any name now. This is just a block diagram. We have a peripheral unit 1, peripheral unit 2. Now, how it works? So I think you can see the numberings. Suppose one interrupt request is coming. This is the first one. We'll see that 1, 2, 3, 4. This is how we'll handle, or we'll understand the operation. So you see that at the very beginning, the peripheral one sends the interrupt request through the interrupt request pin number 1 of this priority arbiter. And just after that, peripheral 2, or in a overlap time fashion, or in a overlap time span, the peripheral 2 is also sending one interrupt request. Now, these two got two interrupt requests, and these two got some priority. So already in our inter-IC bus or in our CAN bus, we have seen that how the priority can be assigned to the devices or to the component. So based on the identifier value. So lowest ID will get the higher priority. This is one concept. Or based on some interrupt types, if you can recall the interrupt lecture of my microprocessor course, where I have discussed about that the interrupt types have different priorities. The NMI has got the highest one, divide by 0 is the highest one, then overflow interrupt, then we have some priority hierarchy. So based on those priority hierarchy, the priority arbiter will handle this interrupt request that is coming through interrupt request pin number 1 or interrupt request pin number 2. So based on this only one interrupt request will be sent to the microprocessor through the pin number 19. So let's say for 8086 microprocessor. So now the interrupt request is placed, and after that the microprocessor sends the interrupt acknowledgement. And finally, from this scenario, we can see that peripheral 1 wins the race, or peripheral 1 has requested with a interrupt type that has a higher priority over the interrupt request that is sent by the peripheral 2. So that is why the interrupt acknowledgement is sent to this pin. This is the 5, state 5, and after that peripheral 1 is communicating with the system bus. That means the data read or write operation are happen or will happen through the system bus. So this is how we can handle the priority related things using a priority arbitrary circuit. So these actually doing the priority resolving circuit or priority resolving function. So the thing I have discussed those are mentioned in this theory. And you see the microprocessor jumps to the related address of ISR, read from the data bus, and ISR executes and returns. The microprocessor will eventually handle the interrupt service request that is being performed, that is being requested by the peripheral 1 through the priority arbitrator. And the microprocessor will eventually execute the thing we have seen in our microprocessor course. This is the last point. This point means that the related interrupt service routine will be read from the data bus from the memory, and that ISS service routine will be executed, and finally it returns to the earlier stage. Next, what if? Now I will show you that I have shown you one scenario where the priority arbitrator is there. But what if we don't have any priority resolver? So this is another technique. What if we don't have that priority arbitration or priority arbitrary circuit or priority resolver circuit? So the alternation is that daisy chain arbitration. Daisy chain arbitration, you know that what is daisy chain? Daisy chain means one after another we connect the components. Okay. You can see that here we are not using any priority resolver circuit, rather directly the peripheral 1 is connected with the microprocessor system. And again with peripheral 1, peripheral 2 is connected. And with peripheral 2, the peripheral 3 will be connected. So this is how we connect one after another. So that means we say, you have seen the chain, right? Chain means the cycle chain or many chain or the ornaments we have, how the ornaments is made. So this is one after another. So this is one component, this is another. So this is how this is called. This is the structure of daisy chain. And daisy, in the earlier days of computer system, the daisy chain architecture was used, where with the peripheral 1, everyone has to communicate with the microprocessor. That means this is the master, you can say. And how the interrupt can be requested? The interrupt can be requested that, okay, peripheral 2 likes to make some interrupt or any request of data signal. So it requests to the downstream. And another thing is that this is the downstream node. And this is the upstream node. This is the upstream considering the microprocessor's position. And what is the main problem of this daisy chain? I think you can realize that if anyone, so this is a single point of failure. So if anyone is disconnected, the whole system will be disconnected from the microprocessor. So this is the main problem of daisy chain architecture. But so in that case, why you may ask that why the designers have choose this daisy chain arbitration? Because in earlier days, the input-output operations was input-output peripheral number of peripherals for input-output operations was not that much used. So that is why this is a simplest architecture where the peripherals can communicate with the microprocessor by using this connecting policy or by using this architecture, connecting architecture.
স্যার ডাউনস্ট্রিম আপস্ট্রিমের কথাটা কি বললেন স্যার?
Okay, so downstream means you see that the flow of the data, usually the flow of the communication. So this is the flow usually. So considering this flow direction, this node has the downstream node here, and this node has the upstream node, this one. Got it?
Yes, sir.
So considering the flow of the communication, considering the flow of the data from the peripheral to the microprocessor, we are defining the downstream and upstream concept. And already I have discussed about the problem that the daisy chain architecture, if any disconnectivity occurs in any place, then the whole daisy chain will be disconnected from the system. Next, so the main pros and cons. So it's very easy to add and remove the peripheral. Of course, after peripheral 1, you can connect peripheral 2, and with peripheral 2, you can connect peripheral 3, peripheral 4. This is a very simple way. So it is easy to add or remove peripheral, no system redesign needed. This is the main advantage. And we don't need any, does not need any rotating priority. Who got the highest priority? The peripheral one got the highest priority, because if it requires to communicate with the microprocessor, it got the highest priority. Yes, the microprocessor concept is, the interrupt concept is also applicable here. So, okay, peripheral one got the highest priority, so it can be connected as the closest to the microprocessor. In fact, from this concept, the cache concept has come. From this concept, from the daisy chain architecture, the cache concept was evolved, because we know the cache is the most closest memory to the microprocessor. Anyway, so we don't need any rotating priority, but the main cons or the main disadvantage of using the daisy chain arbitration is that one broken peripheral can cause loss of access to other peripherals. So if this peripheral 1 is disconnected, if this downstream node is disconnected, the whole peripherals will be disconnected, because they cannot place the interrupt request through this peripheral 1. You can see the interrupt request. So this is another architecture before the priority resolving technique. So before this priority arbitrary technique, this was another architecture. Now I'll talk about another architecture. That is the multi-level bus architecture. What a multi-level bus architecture includes, let's see that you can see, just previously I've talked about that cache memory is the most closest circuit to the microprocessor. You can see. Then after microprocessor, we have the cache, we have the memory controller, we have the DMA controller. And these are connected through a bus. We say that bus name is processor local bus. So this is a highest priority bus. And we have a bridge circuit. This is a circuit, or this is an integrated circuit. And this bridge circuit makes a bridging between another bus, between processor local bus with another bus, that is the peripheral bus. And what is the peripheral bus? The peripheral bus is the bus where all sorts of peripherals will be connected. If you can recall the CAN bus technique, CAN bus for the automotive vehicles, if you can recall that we have a dashboard in one end, And in the other end, we have a low speed bus, and in the other end, we have a high speed CAN. And with the high speed CAN, the most prioritized components were connected, like the engine functions, or the light or AC functions was connected with was connected with the lowest priority part. Now, who made the bridging? The dashboard circuit made the bridge between these two bars. The same concept was designed based on the multi-level bus architecture. This is the most general name, is that multi-level bus architecture. In a computer system, it is also possible, but for a large scale system, this multi-level bus architecture may be designed. So in a multi-level, why it is called multi-level? Because we are using two levels of bus architecture. One is processor local bus, another is peripheral bus. And you see that what sort of components can be connected with which bus. So we don't want one bus for all communication. Peripherals will need high speed processor specific interface, the thing I have talked about in CAN bus. Actually, why we are making this multi-level bus architecture? Because too many peripherals slow down the bus. So if you are using a large scale embedded system, in that case, the data transfer rate will be very high. So if you connect too many peripherals in a single bus, that will slow down the bus capacity or data transfer speed. So what is the solution? The solution is the processor local bus. So it is a high speed, wide, most frequent communication. For making the most frequent communication, we use the processor local bus, and usually it connects microprocessor, cache, memory controllers, etc. But peripheral bus is relatively handles lower speed communication. It's a narrower, less frequent communication. And typically this bus follows the industry standard, that is the ISA or PCI for portability. And for small scale devices, for small scale components, this bus technology can be used. But whatever the thing is that we use the multi-level, there should be, of course, one bridging. This is the most important circuit, that is single purpose processor. You can say this is a co-processor. This is a co-processor that converts the communication between the processor local bus and peripheral bus. And this can be acted as the priority resolver. This can be acted as the priority resolver so that the peripherals make the interrupt request via the bridge, and bridge will make the priority resolving thing on behalf of the peripheral. Then it sends the request to the microprocessor. So this is another structure you should understand. So far we have seen the one structure. This is the typical structure for a computer system. For a small scale computer system, nowadays we are using this. This is the early days structure where we don't have any priority resolver circuit. Next, this multi-level bus architecture is used for large scale embedded system or large scale computing system, where one bridge circuit would be there to make the communication between multi-level buses. So I have given you the structure concept of a computer system where the interrupt can be performed. Now, just a revision that what we have seen in interrupt. We know that, just I have included to make this lecture a complete one. I know that you have already studied this. So we know that the interrupt has the ISR, interrupt service routine. That interrupt service routine is placed into the ROM, and this function is likewise the header file, and we have to call it to some specific interrupt type number or interrupt type identity. And of course, why do we need interrupt? Because interrupt provides an efficient way to handle unanticipated events. Now, this is the revision of basic procedure of interrupt, the 6 points. If you can recall the 6 points that push flag register, IP register value, CS register value, and it goes to a fixed memory location to identify the ISR or interrupt service routine code and reach the address of the associated ISR, then jump to the address and execute the ISR. And after that, after completion of this interrupt service routine, it returns back to pull up the or to pop the flag register, CS and IP register from the stack and continues executing the previous job. Now, three signals should be used for interrupt to the interrupt hardware pins. One is interrupt request for generalized interrupt request. It might be software request or hardware interrupt request, but we have some specific type of non-maskable interrupt that has the highest priority, and that has this, in a microprocessor system we have a specific pin for NMI, but both these interrupts can be acknowledged through one pin, that is the interrupt acknowledgement pin. So these are the revision things I have included, and whenever a microprocessor or whenever a peripheral sends any interrupt request, it should use the INT, then the number of interrupt. You know that the number of interrupt can be in between 0 to 255 for 8086 microprocessor. And of course, at that time, the interrupt enable flag should be set. And these are all revision that we use the n value multiplied by 4 to identify the address of the ISR. And these are the just I've included as a revision to make this lecture a complete one. You can consult with the earlier slide of microprocessor course. But our main concept of this lecture is that to understand the operation of 8259, the 8259 programmable interrupt controller. So PIC. You see that it is a tool for managing the interrupt request, and 8259 is a very flexible peripheral controller chip, and that can handle maximum 8 interrupt requests, but in a built-in feature, it can be expanded for handling 64 levels. So in a system, if you use 8259, that means you can a microprocessor can handle maximum 8 interrupt requests, but it can be expanded for handling 64. How? Let's talk about this point particularly. I'm showing you one figure. You see, next I will come to these points later. First, I will discuss about the 8259 interrupt controller block diagram. Just forget about the peripherals. Let's consider that this is the priority resolver. So earlier we have seen one figure, that is the microprocessor. And with the microprocessor, the priority resolver is connected. Then with the priority resolver, multiple devices, peripheral 1, peripheral 2, peripheral 3. So this is how multiple devices are connected. You see that, or multiple peripherals are connected. You see that I'm just omitting this part because we have only the priority resolver. You can consider this priority resolver. You can consider this 8259 as the priority resolver, and we have the microprocessor. So I am showing you this block diagram to give you one idea that how the structure is designed for the computing system, that with the CPU, the priority resolver or the 8259 programmable interrupt controller is connected directly. And it can exchange the interrupt request and as well as interrupt acknowledgement. But this is the later part. First of all, at the very beginning, the interrupt request should reach to the 8259. That means to handle the interrupt request, we have 8 pins. So that is why the earlier slide we have claimed that maximum 8 interrupt requests can be handled simultaneously by the 8259. Why? Because this 8259 has 8 pins to get the interrupt request. And after that, if it gets 8 requests from each of these pins, then it will resolve the priority. And based on the priority resolving logic, it will identify the highest prioritized interrupt request, and on behalf of that request, it will send the interrupt request to the microprocessor, and it will get the acknowledgement, and accordingly, that interrupt request will be executed. So this is one thing, and how we can expand it up to 64 levels or 64 interrupt requests. So let's see. So 8259 programmable interrupt controller, just I have made the figure mirrored a bit. So you see that we have our CPU, for the interrupt request, and we have the 8259 programmable interrupt controller. This is the master one, and you see 1, 2, 3, 4, 5, 6, 7, 8. And with each of these master, we may connect one slave. So you see that how many slaves we can connect? We can connect 8 slaves. So we can connect 8 slaves, and each of these 8 slaves got 8 interrupt request pin. So 8 by 8, you know that's total 64. Have you got it?
Yes, sir.
Okay. So this is how it can be expanded. It can be expanded to connect 64 peripherals. Total 64 peripherals can be connected with 8259. But in recent days, the recent priority resolver or interrupt types or interrupt controller can handle more than that. I'm talking about considering the 8086 microprocessor, and with 8086 microprocessor, the 8259 programmable interrupt controller is compatible to work, and it can be expanded up to 64 levels. 2 levels, in fact, it's 2 levels, the master level and slave level, but we have the 64 pins total in the second level. So it is almost like another bus technology, that is the inter-IC bus technology. You see that until and unless the master allows, no 8259 that is connected into the slave level can communicate. So this concept is also related to the inter-IC bus. Okay, so this is one thing, the first point about 8259. Next is the second thing is that interrupts can be masked, and interrupts can be masked that this is the statistics. I will show you that which interrupt has given the service, and that can be masked. You know that mask means a kind of blocking, and which interrupts is currently masked and which interrupts is currently unmasked. That information is stored in some register. So that is one point. I will show you the operation. Various priority schemes can be programmed if you use one priority resolver. Now, what sort of priority scheme you can apply? Let's say I will apply some scheduling mechanism like round robin. I will apply the lower identity got highest priority, or the highest identity got the highest priority. So in many ways, or depending on the interrupt types, we have defined some priority. So based on that as well, the priority schemes can be programmed. So that is why we say programmable interrupt controller. And there is a question that whether it's a part of the microprocessor, whether PIC is a part of the microprocessor. No. Originally in PIC, it is available as a separate integrated circuit. It is not a part of the microprocessor. And I have shown you that the functionalities of two PICs in the motherboard chipset. And in some of the modern microprocessors, the functionality of the PIC is built in the microprocessor. It's come with you say that it's in modern microprocessor as is correlated with the operation of the microprocessor. So that is why it works as a coprocessor and it is built in with the microprocessor. You don't need to connect those. But the basic operation performed in this way. The basic operation performed with the way I have shown you in the earlier figure. This is the way. Okay, so I think up to this, I'm stopping today. On Friday, we have a class test. And after the class test, I will discuss about the operation, how the 8259 operation works. And I will discuss about the block diagram. This is the block diagram. I'll discuss about the pin diagram and the operational diagram I'll discuss. And I will discuss about the more details about the registers or internal operations of 8259. So hopefully I will finish it on next Friday. So on next Friday, we have a class test. So you have the class at 2:10 or 2:15. Oh, sorry, 2:30. Sorry, I forgot. So on 2:30, we will start the class test, maybe 30 minutes. And after that, I will finish this lecture on next Friday. So any question? I'm stopping. So everyone knows that on next Friday we have the class test, right, Akib?
Sir, class
Yes,
test
sir.
কতটুক স্যার সিলেবাসটা?
On Canvas, I have uploaded all the lecture slide on IC bus and Canvas. Lecture 8 and 9. Okay.
Okay, sir. Yes.
Okay. So see you on next. Okay. We have a class. We have a lab today at maybe 3:15, right? So we'll have the lab 4 today, inshallah. So see you in the lab, inshallah. Okay. Allah Hafiz.
Assalamu alaikum.
Alright.